What's up, everybody? This is John with John Fair Innovations, bringing you another math lesson. So today I'm going to teach you a little bit about integration by parts. Now, before I get into the video, if you enjoy it, do make sure you hit that thumbs up button, leave a comment on maybe another maths topic you'd like me to tackle. If you really enjoy the video, do make sure you hit that subscribe button so you can stay up to date for all the videos as they come out. Now, today we're going to assume that you have a bit of knowledge in regards to integration and calculus. So I assume that you have some understanding of how integration works, how derivatives work, the power rule, for example, and also some of the trigonometric identities when involving derivatives. So, for example, the derivative of sin is cos, for example. So today what we're going to be using is the integration by parts formula to solve a pretty tricky integration equation. So the one we've got here today is we're trying to solve the integral of x multiplied by cos of x. And what we have here is our formula. So the formula given to us is that the integral of some function of x, f of x in this case, multiplied by another function, g of x, that one's derivative in respect to x. What it will actually turn out to be is we will end up getting f of x, so a function of x, multiplied by a function of g of x, so there's different function, minus the integral of the derivative of function x multiplied by g of x, all to the derivative of x. And so we can actually apply this to our problem in order for us to solve. So what we do is, firstly, we take our problem that we have and we can see if we can apply it to our formula. In this case, when we're using integration by parts, what we're looking for two functions of a variable multiplied by one another. In this case, we're using variables of x. This could easily work with u, it could work with v, w, it doesn't matter what letter you're using. In this case, we're using x because that's obviously the most common. So now what we're trying to do is we are trying to see if we can apply it. So what we have to do is we have to break our problem into two functions, function f of x and function g of x's derivative. So in this case, we can clearly see that we have two potential functions that we can have here. We can have x and we can have cos of x. Now, generally the rule is you make f of x the simpler one. So in this case, we've got x, so we can apply this as our function x. So firstly, what we're going to do is we're going to let f of x equal x. Now, if we look at the rest of our formula, we can see that we need to find the derivative of this. And this is why we pick the easier one, because we know from our power rule that the function x's derivative, derivative of x, I should say, is just going to simply be 1. So we can easily have two components of our formula. So next, what we have to do is we have to look for our g derivative of x. So in this case, it's going to be the other part of what we have left over of our function in our integral, which is cos of x. And so what we're actually going to have to do with this one is we're going to have to find the integral. But firstly, we let g derivative of x equal cos of x. And now all we simply do is we use the integral of this. In this case, knowing our trigonometric identities, we are going to know that the integral of cos x is simply going to be sine of x. So now we have all our components that we need in order to use this formula. So what we simply do now is we simply substitute it in for where we would in our formula. And hopefully it makes it quite nice that we can solve. So we start writing in. So our first part is function x. So we know that function x is in fact going to be x. The next part is g of x. So this is simply going to be sine of x, because that's what we worked out before, minus the integral of the derivative of f of x. So in this case, we know that one to simply be 1. And we multiply this by g of x, which again we know to be sine of x. And this integral is going to be in respect to x, because that's the variable we're using. So now we try and simplify this. Well, x multiplied by sine of x, we're going to leave as is. And then what we do is 1 multiplied by sine of x. Well, 1 multiplied by any number is going to be itself. So 1 multiplied by sine of x is going to be sine of x. So that's going to leave us with the integral of sine of x in respect to x to solve. And again, what we simply use is we simply use our trigonometric identities, because we know how sine x and cos x work when they're being derived, and we're finding the integral of these. So the integral of sine of x is in fact going to be negative cos of x. So we can rewrite our equation to read x multiplied by sine of x minus negative cos of x. And we're also going to add a variable called c. Now, when you're finding the integral, you simply have to add this, because when we find the derivative of a function, what happens is that if you have a normal digit, let's say 6, for example, the derivative of this in respect to a variable like x, for example, will give us a 0. So it won't actually be represented in a function that's already been derived. So if we're trying to find the integral of this, we have to account for the fact there could have been a constant involved. So c just means some sort of constant. And now all we do is we simply simplify our equation and we're done. So it's going to equal x multiplied by sine of x. We've got 2 negatives in front of the cos, so that's going to turn into positive cos. So plus cos x plus c, where c is simply our constant. So that's our answer. We've got x multiplied by sine of x plus cos x plus c, where c is a constant. Well, there you have it. Hopefully you enjoyed that. Do practice it yourself, because honestly, that's the best way to learn these things. As I said before, the key component about integration by parts is knowing that you're looking for 2 functions multiplied by the same variable. In this case, we could break it apart as x and cos of x. But always stay safe, be kind to one another, and I'll see you next time.